Hello Math 1550 students. We are nearing the end and you are working on your final project for the course, the technology project, and I thought I wanted to give you a little help with it. So I have here a book and something to write with, and I also have the ebook and my computer running, and thought I would prepare a little video for you so you can work on this assignment. So if I go to Blackboard, if I go to the assignments, again, it's here at the bottom of the Assignments tab, the Final Project in place of a fourth exam. So you can use StatCrunch or Excel or some other piece of technology, but I want you using computer software. That's the idea of the project. And there are two technology projects listed, Chapter 8 and Chapter 9, or you could do Chapter 7. And then I asked you to do one homework problem from each of the remaining sections using the technology. So I thought I'd show you, if you look in the book, here's the homework that was due today, Chapter 11, Section 2. And we had a few problems to do, but what I want you to notice is, right before you get to question 1, and this goes throughout the entire book, there's a Using Technology blue box. And if you're using StatCrunch, it's right here at the bottom. I think some of you have used this paragraph before for TI 8384, but there's also StatDisk and Excel. So if you're going to use one of these technologies, I guess directions are right here in terms of what you have to do for a given problem. Okay? And I thought maybe what I would do, rather than do these problems for you, is work on Chapter 9 a little bit. Here's Chapter 8. Let me jump to the Chapter 9 technology project, which it says is on page 490. So I'll go back to the book, type in 490, and I'd like to take a look with you at the project and just see if I can make a few comments that'll help. So here's the technology project, and I think I'm going to use StatDisk, or no, I'll use StatCrunch, what comes with the Pearson website, as my technology. But you notice what it says. It says in example 3 of section 6.2, we noted that bone density test scores are measured as z-scores. Yeah, z-scores back in chapter 6. I remember studying that. And when the book taught z-scores, they like to mention bone density scores. My mother has had these bone density tests. She suffers from osteoporosis. And when they give you a result of the test, what they actually give you is a z-score. So here's example 4 talking about it, and let me go to the next page, 251. A bone density test reading between -1 and -2.5 indicates the subject has osteopenia. Find this probability of that happening. And so you can remember these familiar pictures, and we talked about how 15% of the tests, or 15.25%, will end up in that region. Okay, so Chapter 9 project mentions this and says, okay, let's go ahead and analyze what happens in the following scenario. We're going to give some treatment to a group of 10 individuals, and we're going to also have a placebo group. And suppose that the treatment doesn't do anything. Sometimes that happens. Sometimes someone claims, hey, we can treat bones in the following way and it works. And let's do an experiment to demonstrate that it works. Sometimes it has no effect. And this is going to be a situation where we demonstrate a situation where it has no effect. So what they tell me to do is click on Data, click on Simulate Data, and select the menu item of Normal. We're going to generate 10 sample values from a normal distribution with a mean 0 and standard deviation 1. Okay, so I'm going to launch StatCrunch here. And to get there, I'm going to go to the main menu of my StatLab. StatCrunch is down here. And when I click on this, first it's going to give me the option of if I want to actually view data sets from the textbook. I can do that here. But now I'm going to go directly to the website, and I'm just going to go ahead and click on Open StatCrunch. So it launches it. And so I have this little spreadsheet here. And again, all the directions I need are right here. Click on Data, click on Simulate Data, select the menu item of Normal. Alright, I can do that. So I'll click on Data, click on Simulate Data. I want a normal distribution. It's going to say how many rows, how many columns. Well, we're supposed to do 10 rows in the first column. Mean 0, standard deviation 1. And that's pretty much it. Column name, I'll just leave it. Well, no, I'll go ahead and do this. This is optional, but I'll say that this is the treatment group. Compute. And so it gave me some data. There's the treatment group. And now I'm going to go here and I'm going to do the same thing. So I'm going to go Data, and I'm going to again do a simulation. Normal distribution. This time I'm supposed to have 15 rows. And this is the placebo group. And so there's 15 data values there. And so I want to talk a little bit about what it is we're doing here. So let me go to the paper. And so in Chapter 9, remember the idea was we are testing 2 populations. And so in this chapter problem, there's the treatment group versus the placebo group. And we're estimating means here, okay? Now we know something about the means. We know that mean 1 and mean 2 are both equal to 0. We know that. That's the way we designed the data. We typed in mean equals 0 in each of those cases. Okay? But a lot of times what happens if you're testing a treatment is you think that, oh, this helps bone density. And so maybe my claim might be that mean 1 does not equal mean 2, right? So my null hypothesis would be mean 1 equals mean 2, and the alternative hypothesis would be that the mean 1 does not equal mean 2. Of course, another way to do this is you say mean 1 minus mean 2 equals 0. There's your null hypothesis. And then the alternative is that mean 1 minus mean mu 2 does not equal 0. Right? And then what we did was we did a test statistic, or some of you use the technology to test the claim that these means are different. So I'm going to go ahead and make a test. I'm going to test. We would need the t-statistics because we're talking about means here. Using the data that we have, select the values from the treatment group and the placebo group. I'm allowed to pool the variances. I don't need to do that. And I'm going to go ahead and compute. Oh, wait a minute. Hypothesis test, yes. Mu 1 minus mu 2 equals 0, or mu 1 minus mu 2 does not equal 0. I'm going to compute. And they gave me a p-value of 0.93. That's a very high p-value. So we would fail to reject the null hypothesis here. And so I guess what I could do is I could say that we took N1 is 10 and N2 is 15, and what I would say is that my p-value was about 0.93, and so we fail to reject the null hypothesis here. And so it is possible that the two means are the same, that both groups have the same mean bone density. Now, because I want to emphasize that we either reject or, in this case, fail to reject the null hypothesis. And if you fail to reject, what I would say is there is not sufficient evidence to reject the claim that both groups, meaning the treatment group and the placebo group, have the same mean bone density. Now, what's interesting is, again, that we know the two groups have the same mean bone density, so how would we reject it, right? And so one of the things that the project gets into is, well, how often do you reject the bone density groups? What I did after doing that experiment is I did it again, and I want to show you what StatDisk looks like now. StatCrunch. You'll notice I have another treatment group and another placebo group, and a third treatment group and a third placebo group. And just like I did the two sample t hypothesis test, and I got a p-value of 93%, for the second pair, treatment 2 and placebo 2, I did it again and I got a 96% p-value. Again, that's pretty high. But the third time I did it, I got a p-value of 37%. Now, I still failed to reject. Why do I fail to reject? Because remember that the project asked me to test with a 90% confidence level, so a 10% significance level. If I look at the e-text carefully, here, let me go back to the project page for just a minute. So again, it was on page 490. So I'll go back to page 490. And it said, use a 10% significance level. So if any of these p-values had been less than 10%, then I would have rejected the claim that the means are equal. But I know they're equal. It says, if this experiment is repeated many times, what is the expected percentage of trials leading to the conclusion that two population means are different? So again, I've done it 3 times here, and I've failed to reject the null hypothesis each time. But what if I did it many times, and in fact, later, you're going to repeat this experiment 20 times and try to say what happens? But already, if I understand that we said that the significance level, which is alpha, is 0.10 or 10%, okay, part B, okay, this means that in 10% of the hypothesis tests we do, we would, and I'm going to put in parentheses incorrectly, because it would be incorrect, reject the null hypothesis. Again, we know the means are equal. If we reject the null hypothesis, that would be saying, no, they're not equal. That'd be what's called an error. The fact that it's incorrect, when you incorrectly reject the null hypothesis, this is what's called a type 1 error. And some of you that are in the sciences will hear about, or social sciences, you'll hear about a type 1 error. That's when we incorrectly reject the null hypothesis. And one nice thing is that this gives new meaning to what significance level is telling you. It's telling me, oh, there's only a 10% chance, or there is a 10% chance that I will reject the null hypothesis. So I want to go back to the project because it asks, in the project I was just answering B with you, but I'd like to talk about part D also. Here, let me go there. So on the next page, it's funny, it said, the other thing it said in part B is, how does this relate to a type 1 error? Well, it's the 10% is the probability of it being a type 1 error. Part C, if your generated data should lead to the conclusion that the two population means are different, would this be correct or incorrect in reality? We know it's incorrect, because that's the way we constructed the data, with the same mean. Part D, if part A is repeated 20 times, what is the probability that none of the hypothesis tests lead to rejection of the null hypothesis? I have an alternate question for D. Okay? Part D, okay? Suppose we repeat this experiment 20 times. Now again, so far, to be clear, I've done the experiment in StatCrunch 3 times. 3 times I made a treatment group and a placebo group using that random normal with mean 0 and standard deviation 1, and 3 times I computed the p-value, and it was high each time, but this one is not as high as the other ones. And actually, one reason that those p-values came out the way they did, if you look at, by hitting the stat button, summary stats of the columns, and I can select which columns. If I hit Control A and select all the columns and hit compute, it gives me some interesting information. Here are the 6 columns. Look at the means. Columns 1 and 2, the means are very close. Negative 13% and negative 10%, right? Columns 3 and 4, they're very close. 0.19 and 0.21. At least compared to 5 and 6. 5 and 6 we have just around 0, a little bit negative, and 0.3. That's a significant difference. Well, it's a difference. And that's why the p-value was lower there, 37%. If I happen to keep going, maybe I would get a situation where the means are so far apart that the p-value gets below 10. That would be an example of what's called a type 1 error. And so really, when I look back at the project and the problem states, what's the probability that none of the hypothesis tests lead to rejection? Maybe before I answer that, I can answer this question. Suppose we repeat this experiment 20 times. How many type 1 errors would I expect? Well, to answer that, one simple solution would be take your 10% of 20, or times 20, and get 2. I'm thinking I'm probably going to get around 2 type 1 errors out of the 20. You guys are going to try it in part E and see what you get. Okay? But the other thing that part D asks is, what is the probability of getting no type 2 errors? Okay? I'm sorry, no type 1 errors. We didn't talk about type 2 errors here. And so what I'm going to do is something we did in chapter 5. I'm going to define a random variable. I'm going to say let x represent the number of type 1 errors we get in 20 trials. So I did the experiment 3 times. If I do it a total of 20, and so what do I know about x? Well, I know it's less than or equal to 20 and greater than or equal to 0. That'd be the extremes. That'd be if I got all the every time I do it I get a type 1 error, or I might not get any, right? Or something in between. I'm saying 2 is the most common, but what I'm doing here is the probability that x is equal to 0. That's really what part D is asking. Probability of no type 1 errors. Right? And the formula I can compute because I understand x here from chapter 5 again is what's called a binomial random variable. And so the formula for that, the probability of x equaling 0 is 20 choose 0 times little p, the probability, which we know is 10% to the 0, times 0.9 to the 20. Okay, so I could work that out and see exactly what I get. So on my TI calculator, I can tell you that those first couple expressions, anything to the 0 power is 1 and 20 choose 0 is also 1. So all I really have to type in here for keeping it straight is just 0.9 caret, which means to some power, to the 20th power. And that'll tell me that there's approximately a 12% chance of getting no errors. I'm going to show you how to do that on StatCrunch as well. What we have is we have a binomial random variable. So I can go to StatCrunch and I can ask it to do well, data, and let's do simulate a binomial random variable. Number of rows, don't need it. Number of columns, don't need it. But what I need here is I need n, and we're going to do 20 trials. P is 0.1, and what I want is I want to compute. I need a row. I need a column. So to see what to do for the binomial random variable, I can go to my textbook, and again, if I just look at the pages right before the homework, they have a little technology box that tells you everything you might want to do. So let's see. Here we are. Binomial probability distributions start on page 210. And if I go forward just a few pages, I'll get to where the homework is. And there at the top of the screen on page 217, I see some info on using technology. It says click on Open StatCrunch, which I have, Click on Stat, Calculators, Binomial. So that's pretty nice. Let's do that. StatCrunch. Let's go Stat, Calculators, Binomial. And here, this little calculator has everything I want. My P is only 0.1, my probability of success. N should be 20. And what I'm computing here is the probability that X equals, say, 0. 12%, that's what I did last time. I mentioned 2 as being the most likely thing to happen. What's the probability of equaling 2? It says 28%. And you can see that the probability really goes down from there. But anyways, this gives you an idea that when you do your 20 experiments, you may get type 1 errors, either 1 or 2 or 3 or 4. Some of you may get 0. It's unlikely you're going to get much more than that. Could happen. Anyways, I'm curious to see what you get when you finish this part of the project. So I think I'll do one more thing with you here. I want to talk about the Chapter 8 project a little bit. So the Chapter 8 project is on page 437, talking about the Chapter 8 chapter project. It says we're going to have 41 different election ballots, and the question is, how many of those are going to have Democrat at the top? And so I just thought I'd show you kind of what's going to happen. I mean, if we think about it, again, we have a binomial situation. It's either Republican or Democrat. This time, instead of having 20 trials, there are 41 ballots. This time, instead of having 0.1% chance of success, according to the book, 50% chance of success. And so now, it seems to me that the book is asking the question, what is the probability that X is bigger than or equal to 40? What's the chances of, out of the 41 ballots, 40 or 41 of them, either one, have the word a Democrat at the top? What I could ask you is, hey, what's the most likely number of Democrats you'd get? Well, half of 41 is 20 and a half, so notice that the picture shows that the most likely thing to happen is right around 20 or 21. But when we go to compute the probability of X being either 40 or 41, look how low the probability is. 1.9 times 10 to the negative 11th. That's ridiculously small. It is extremely unlikely that when you have 41 ballots, that 40 of them, or 41 of them, would be saying Democrat. So, while this is not exactly what it says to do, this gives you the idea that even if you do this 100 times, you're probably not going to find any of your experiments where there are more than 40 successes in this case, more than 40 Democrats. Probably not going to happen. So, wanted to bounce that off you. I'm hoping that this may be enough at this point that you can go ahead and finish the assignment. If you want to take pictures of your work and scan it in, that's fine. If you want to just attach some kind of a Word file, that's fine. But wherever it is, you can click on Final Project and submit it when you're done. And that's the last major grade of the summer. I just want to say it's been an absolute pleasure working with you, and I hope that you learned a lot, and I wish you all the best in your future studies.